So the main concept in this chapter, chapter 6, are work and energy, power. And in this video that I'm going to share with you right now, we will introduce all this work, energy, power quickly on this video. Let's start with it.
When I say work, what's the first thing that comes to mind? Maybe a cubicle or a briefcase or that history exam that's coming up soon. But if you're a physicist, work has a very specific meaning, one that has very little to do with spreadsheets or the fall of the Roman Empire. Today we're going to explore that definition and how it connects to one of the most important principles in physics: conservation of energy. We'll also learn what physicists mean when they talk about another concept that comes up a lot in daily life: power. So let's get to work.
Too loud.
So far in this course, we've spent most of our time talking about forces and the way they make things move. You need to understand forces before you can understand work, because work is what happens when you apply a force.
So she's going to talk about work and forces before work, and then comes energy.
Over a certain distance to a system. A system just being whatever section of the universe you happen to be talking about at the time.
So the word system, we use it a lot in physics. A box, a car that you're moving, something that you are dealing with. You choose it, it's a part of the surrounding environment. Maybe you are a system if you are studying the forces acting on you. So a system, something that you are, like a box, for example.
For example, if you're using a rope to drag a box across the floor, we might say that the box is your system, and the force you're using to pull on it.
Oh, the box will be your system, and system include the box. And regarding that, you have surface here, horizontal surface, and this is called external force exerting on that system. Why I call this external? Because it's outside the system that I already chosen before. Okay, guys? So you choose the system that you are focusing on, that you are studying forces acting on it, and any other forces from outside will be an external force. That's why we call it an external force.
It's an external force. So let's say you're pulling on this box system by dragging it straight behind you, so the rope is parallel to the ground. If you're using the rope to pull the box for 1 meter, we'd say that you're doing work on the box. And the amount of work you're doing is equal to the force you're using to pull the box times the distance you moved it.
Again, she said in the beginning that work may mean that you have exam history, you have something to do at home, at work. You go to work, you come back from work, but work in physics is different. Work in physics mean force multiplied distance, force multiplied by distance.
For example, if you pulled the rope and therefore the box with a force of 50 newtons while you moved it 5 meters.
Oh, this is an example. If the acting force, applied force is 50 Newton, and the acting force for 50, if you're 5 meters, so the work done force and have work, they must be parallel in the same line. The acting line is the same for force and distance. They must be parallel. We will see that in details in a short while.
Then we'd say that you did 250 Newton meters of work on the box. More commonly, however, work is expressed in units known as joules.
Work is measured in joules, which is equal to force multiply joule equal work equal force multiply distance, force in Newton and distance in meter. Newton times meter give us a joule, which is the Newton of the unit of measuring unit of work.
Now, sometimes the force you're applying to an object won't be the exact same direction as the direction in which the object is moving. Like if you try to drag the box with your hand higher than the box.
So this is another situation. The external force is not parallel to the horizontal surface. What would happen then? I said before, to have work, the applied force must be parallel to the distance moved. In this case, the external force, the net external force, is not parallel. What we are going to do, let's see.
So that the rope was at an angle to the floor. In that case, the box would move parallel to the floor, but the force would be...
See, the movement is parallel, but the force is not parallel to the horizontal surface.
At an angle to it. And in such an instance, you'd have to use one of the tricks we learned earlier when we first talked about vectors. Specifically, you need to separate the force you're using on the rope into its component parts. One that's parallel to the floor and one that's perpendicular.
So, the net force, the outside force, on the two directions, one parallel and the other one perpendicular. Let's see that.
To find the part of the force that's parallel to the floor, that is.
So this is system, that's external force. This is the net external force. So I'm going to analyze this force. One component will be parallel, and this will cause the motion, and the other one will be perpendicular to the horizontal surface, and this does not cause any motion. Okay, guys?
Is the one that's actually pulling the box forward.
Again, she said very important word. This is the actual force. This component parallel, this is the actual component of force that is pulling the system. The other one that's parallel, it's not affecting on the system, or it's not affecting on the pulling the system, movement of the system horizontally on the surface.
You just have to multiply the magnitude of the force by the cosine of the rope's angle to the ground.
Again, we take this before in vectors and analyzing vectors. We multiply to have this one that is adjacent to the angle. Let's go back a little bit. Yeah, that's it. To have this component, the x component, or the component that is parallel to the horizontal surface, this one is adjacent to the theta. So to find this component, it will be cosine theta.
The ground. You'll remember that we typically designate an angle in the system as theta. So to calculate the work you did on the box, you just multiply the horizontal component, or f times the cosine of theta, by the distance you move the box. That's one way physicists often write the equation of work. They'll set it equal to force times.
So this is the general formula to find work. Work equal force multiply distance multiply cosine theta, where the theta is the angle between the direction of force and the direction of movement. Okay, guys? Theta is the angle between the direction of external force, net external force, and the direction of movement.
Distance times the cosine of theta. And that equation will fit any scenario that involves a constant.
Again, this is the general equation. It will fit any scenario. It's not only for this scenario with parallel, it can also work with the horizontal one. Let me start the board with you. I have to start a new one with you, I think, because this is, I'll finish that. I have to start a new one. Let's assume we have a surface, horizontal surface like this one, and we have a cube like this one, and we have a force, external force, and that would be the external force acting on it. Right now, the force in the same direction of movement, theta equal to what? Who can tell me? What is theta is equal to in this case? Theta equal to what?
0.
Yes, bravo. Theta equal to 0. Okay, and let's apply the general formula. The general formula would say that work equal to force multiplied distance multiplied by cosine theta, which is equal to theta. If you use your calculator right now and you type cosine 0, cosine, the angle here is 0, so cosine theta equal to what? Cosine 0 it will be, sorry, I have to type 0. Cosine 0, the angle is 0, equal to 1. So we will end up to this formula, which is work equal force multiplied by distance. Okay, guys? So this one is a special case from the general one. So this is the general formula to calculate work. that will fit into any scenario, as she says. Let's go back to the video.
Force being applied over a certain distance. But what if that force isn't constant? What if, say, you started out pulling hard on the box, but
So the force is not constant. You don't have it, actually. We will have it in some problems, but we'll take it later, but not here.
bit of distance. And if you've watched our episodes on calculus, then you'll know that there's a faster way to activate that force relative to the work. Because you know how we just said that joules are the units of work? Well, joules are often used as the units for something else, energy. And
so we have two terms here, work, and we have understood it, which is talking about the force acting on a system and cause the system to move for a distance. So we will multiply the horizontal force, the component of horizontal force, multiplies the distance covered, will give us work. Now we will talk about energy. They are so related.
work uses the same units as energy because work is just a change in energy. It's what
That's the difference. Work is a change in energy. For example, you have internal energy right now in you, 1000 joule. You go to play something, or you go to study or do some work. So your energy decreased from 1000 to 800 joules. This change in your internal energy is performed as work. So work is the change in energy. That's the main difference between work and energy. They are the same. You can think that energy is your bank statement, the amount of money you have in the bank. If you take some money to have food, you take some money to buy a car, so your bank statement decreased, your energy decreased. And this amount of decreasing, you use it to do work or to do something outside the energy. So energy is the amount or ability to do work. And the change in energy means what? Means or will appear in the form of work. Again, energy is not something that you can see it, but work something that you can see it. The bank statement, I don't know what's your bank statement, but I can see that you are buying a new car, so I can know how much money did you spend on this car. So I can see you do some work, so I can calculate the work that you're doing, and I can know what is the change in your energy. But the total energy that you have it, I can't calculate it without calculating work. That are some differences between work and energy, guys.
happens when an external force is applied to a system and changes the energy of that system. In fact, that's one of the ways to define energy. It's the ability to do.
Yes, it's a general thing, okay? Ability to do work, this is energy. But work is a change in this energy. We can calculate work by the previous equation. So energy is something, it's not, most of the time, it's not visible, and a change in energy will appear in the form of work.
There are all different kinds of energy, but in this episode, we'll mainly be talking about two of them. Kinetic energy and potential energy. Kinetic energy is the energy of motion. When the box was resting on the ground, we'd say that it had no kinetic energy. But once you applied a force and it started moving, it did.
So right now we are going to calculate the total energy. This is not work. We are calculating energy of something. If you have a ball that is moving with a different speed, so it has some kind of energy. We call it kinetic energy, and we can calculate it in this case because we know the velocity that is moving with. And another one is called the potential energy. We'll come to it later.
Did have kinetic energy, and the energy of the box changed, which means that you did work on it. More specifically, the kinetic energy of an object is equal to half of its mass times its velocity.
Times its velocity squared. So that's how we calculate kinetic energy. Again, we can calculate it because we can see the ball or the car is moving. We can define its speed. So this is only one form of energy that the car may have. The car may have, or the ball may have, different forms of energy, but one form of energy we can calculate it because of the speed of or because of the motion of the object. So if we know the speed of one object, we can calculate its kinetic energy multiplied by, I will square the velocity multiplied by half mass. By this way, I will find the kinetic energy.
Squared. If this looks familiar, that's because it comes from applying both Newton's second law and the kinematic equations to the idea that work is equal to force times distance. So, if the box has a mass of 20 kilograms and at some point while you're dragging it, it reached a velocity of 4 meters per second, we'd say that its kinetic energy at that moment was 160 joules.
Again, work energy any work, any energy that you will emit it will be in joules. So kinetic energy in joules, potential energy in joules. Any kind of energy is in joules.
Then there's potential energy, which actually isn't what it sounds like. Potential energy isn't potentially energy, it's potentially work. In other words, potential energy is energy that could be used to do work.
So potential energy is energy that could be used to do work. Let's see that.
One common type of potential energy is gravitational potential energy.
Gravitational energy is not only one type. There are several types of potential energy. One of them is gravitational. Another one will find elastic potential energy. Chemical energy is a different or a third type of potential energy. Again, guys, potential energy is energy that we can use it to do work. It's stored energy. It's stored energy. We'll talk about the first one here. Well, first type of potential energy. Again, potential energy, you may say gravitational potential, you may say elastic potential, you may say chemical potential, and many types of potential energy. And it means potential energy, it means energy that is stored and it can be used to do work. That's the meaning. That's why we call it potential
energy. Basically, the potential energy that comes from the fact that gravity exists. If I hold this book about 1 meter above the ground, we'd say that it's got gravitational potential energy.
Oh, that's very important here. You see this book, it's away from the resting point, which is the ground, 1 meter away from the ground. Right now, this book has the ability to do work. And the evidence, if she lit the book will fall. So the book is doing work after leaving it. So right now, we can say that the book has the ability to do work. The work is moving downward toward the Earth surface. So right now, it has a potential energy due to gravitation. The book will not fall down without gravity. So the gravity make this book gain some kind of energy. That's why we call it gravitational potential energy. Again, the objects will gain this kind of energy according to existence inside the gravitational field. If you are away in the outer space, if you are in some way, there is no gravitational for Earth or the moon or sun or any other kind of gravitational energy or any other kind of gravity, so this book will not fall in any direction. It will stay as it is. In this case, there is no gravitational potential energy. So gravitational potential energy appears as a result of gravity. That's why we call it gravitational potential energy.
Because if I let it go, gravity is going to do work on the book. Gravity exerted a force that moved it to the ground.
So the book falls down by force of gravity. So we say that gravity exerted force on the book and caused it to move downward. Gravity, I said again, gravity exerted force on the book and caused it to accelerate. So before you let it go, we know, according to the force of gravity, it has a gravitational potential energy. How to calculate it?
If the book hits the ground, though, we'd say that its gravitational potential energy is 0 because gravity can't do work on it anymore.
Yes. If it reaches the rest point, which is the floor that you are sitting in or standing on, so but gravitational potential energy is 0. Why? Because gravity can't do any force, any work on the book and make it move any further distances. So gravitational potential energy in this case will be 0.
More. Calculating gravitational potential energy is easy enough. It's just the force of gravity on the object, so the object's mass, times small g, multiplied by the object's height.
So again, to calculate potential energy of gravity, because we have, as I said before, we have potential energy, elastic potential energy, and we have chemical potential energy. But right now we are talking potential energy according to the force of gravity. If we want to calculate it, we will multiply mass, multiply small g, which is gravitational or acceleration according to gravity, and the height of the object. And the height here, the perpendicular distance between the position of the book, for example, or the object, and the rest point. This rest point could be the floor, ground on the street, could be the top of the so it will be the floor that you are settling on, and the gravity, if this object reaches this floor, the gravity can't do any further work on that object. This we call it reference point. Here, the distance between the object and the reference point,
or MGH for short, which means that just by knowing that this book's mass is about a kilogram and that we held it.
That's it. That's reference point. This could be a table. This could be a floor. This could be anything. But if the book reaches this point, we call it reference point. The gravity can't do any in this object and cause it to move any further distances. So that we call it reference point. This is very important, guys. It's not fixed point. It's according to your system that you're using, the place that you are sitting in. As said again, this book may fall to the table, surface of table, may fall to the floor of your apartment, may fall to the ground, the street on the ground, floor of the street, and so on. So that's called a reference point. So the height here is 1 meter, for example. Gravity is constant, 9.81 meter per second square, almost constant. And the mass is 1 kilogram, and the height would be 1 meter. And then we can calculate potential energy according to gravity.
About a meter above the ground, we can calculate its potential energy, which is 9.8 joules. Another type of potential energy that shows up is spring potential energy. Despite its name, it's not a seasonal thing. And yes, I really made that joke. Rather, it's the type of potential energy that's specific to springs. The force of a spring is equal to the distance by which it's either compressed or stretched times a constant that we write as K. This equation is known as Hooke's law after Robert.
We have covered almost of the chapter. Let this to later time. So let's go back here and start with this one. So I've covered most of this one. I didn't talk about conservation of energy. I didn't talk about power, but I talk about work and energy, different types of energy. And I talk about kinetic energy. I talk about potential energy according to gravity. There is another one. We'll see if we have it or not. And work. So let's start with this one and slow down a little bit. Let's start with, okay, we don't have someone here. Not this one, I'm sorry. This is the physics session. عبد الله الملحم زهير. عبد الله يا عبد الله. Fix your mic, Abdullah. We can't continue like this. Ahmed Al-Mullah.
Yes, I'm here, Mr.
Okay, Ahmed.
Okay.
I want you to read the first slide here. Read it.
Okay. While most people feel that work is done when you work on a problem or do homework, physicists say work has only been done when a force is applied to an object and the object moves in the direction of the applied force.
Yes, this is very important. The object is moving in the applied force, and the law is formula work equal force multiplied distance. If they are in the same direction, work equal F multiplied D. Newton force is measured in Newton and distance measured in meter, which is equal to joule. Thank you, Ahmed. Next one will be Ahmed Tawfiq. Ahmed Tawfiq, read this one.
Sir.
Read this one, Ahmed.
The figure below illustrates work being done as a force pushes a box to a displacement. The work done equals W times force times distance.
Yes.
The dimensions of work are force, newtons, times distance, meters. The product of the two, newtons times meters, is called the joule, in honor of the physicist James Biscuit Joule.
So this is the name. Again, you see here the force is constant. The length of the force vector is constant. So we use this rule when the force is constant. If the force is not constant, we have other calculations. But the force is constant and will cause the system to move a distance d. So we multiply d, they are in the same direction. We will use this formula. To calculate work, work will equal force multiply distance. Thank you, Ahmed. Faisal? Faisal,
Yes.
read this slide, Faisal.
A joule represents a relatively modest amount of work. You do a joule of work when you lift a medium-sized apple through a height of 1 meter. The table below provides some examples of the typical amounts of work.
Yes. Joule, again, you as a student of physics or a physicist, you have to understand the meaning. If I tell you 1 meter, in your mind it comes to you 1 meter equal to what? Maybe the length of your arm, a little bit greater than or longer than the length of your arm. If I said 1 kilogram, you know how many tomatoes, maybe 4 apples or 5 apples make 1 kilogram. So if I said 1 joule, what is the work 1 joule is equal to? So he give you, this is a modest amount, small amount. 1 joule is a small amount. And he gives you some amount here of the unit joule. Annual US energy use, 8 multiplied 10 to the power 19. This is the United States use of energy. You have breaking a bond in DNA 10 to the power negative 20. I want something that is 6,000. Lighting a 100-watt bulb for 1 minute is 6,000 joule. So again, if you have a bulb lighting, you know the bulb, light bulb, 100 watt for 1 minute, this is equal to 6,000 joule. A human heart beat is half joule. You know the heartbeat view, only one heartbeat is equal to half joule. And melting an ice cube is only few centimeters in few centimeters. It requires 10,000 joule. Daily human food intake, the food that you are take daily, is about 10 to the power 7, which is 10 million joules. That's what you have, the food that you eat it daily, intake energy. Burning one gallon of gas is 100 million. 1 gallon of gas is 100 million, generates 100 million million of joules. So this is some typical amounts of work and their corresponding amount in joules. This is important to understand how it works in life, daily life. Hassan? Yeah, Hassan. Hassan, yeah, Hassan. Hassan is here, guys?
Yes, yeah, mister.
Okay, Hassan, can you read, please?
By the definition of work,
This one, it work in
okay, it
maybe.
may come as a surprise that no work is done while holding a heavy object such as a suitcase. By the definition of work, because the suitcase doesn't move, no work is done. However, you become tired because your muscle cells are doing work holding the suitcase.
Oh, this is very important. If you are holding a suitcase and you're moving, is there work done or not? Again, this is very important, guys. Let me draw it for you. So we have the same floor here. This is the floor. And we will have a suitcase here. This is a suitcase. Okay. And you are moving in this direction. This is the direction of movement. You move in this direction. But the force is not in this direction. The force is upward. Because you hold the suitcase with your hand. And your hand exerts force upward. This is your force of your hand. You hold the suitcase upward. Okay, guys, you hold it like this. This is the man. And this is how we're holding the suitcase. Okay. So he's holding the suitcase in his hand, and the force of holding the suitcase is upward, and this is the direction of movement. G. Again. G. I want to find a solution for writing in this screen. So The force here is perpendicular. If we apply the general formula that we talk about it for calculating work equal force multiply distance multiply cosine theta. Theta here is equal 90 degrees. So we'll type it like this: force equal multiply distance multiply cosine 19. So cosine 19 is equal to what? To 0. So work will equal to 0. Mister, I feel tired. I carry a heavy thing and I walk. There is no work. According to this force didn't do any work. But other forces, maybe the forces of your leg muscles, some forces in your leg here is acting in this direction, will do work. Okay, but the force of your arm upward on the case didn't do any work, didn't perform any work on the case. Okay, guys, so that's very important. If the force is perpendicular to the direction of movement, the work according to this force is equal to 0. Maybe some other forces in some other places in your body exert force in the same direction of movement, then thus the work will not be equal to 0. But according to your force in your arm, it's equal to 0. Okay, what is it? Okay. Next one after Hassan. Okay, this one. After Hassan comes Karim. Karim,
Yes.
read it.
Notice in the from the beginning or from the second?
Yes, from the beginning, in the case.
Oh. In a case such as this, only the component of the force in the does work. Notice in the previous figure that the component of force in the direction of displacement is F cosine theta. Therefore, the work equals F d cosine theta.
Yes. So we talked about this and we explained it, and also this is called the general formula. Cosine angle between the force and displacement. Again, this is very important. Cosine the angle, theta is the angle between force and displacement. We have indicated something like this. So we have it here. Force, and this is angle theta. Theta is between less than 90 and greater than negative 19. So this is theta. Theta in this case, remember, it means by this, it's from 0 to 90 and from 0 to negative 90 in the other side. If theta in this direction here, in the first quadrant and the fourth quadrant, we can do a positive work. This will be a positive work. This is positive work. If the theta is equal negative or positive, positive means upward, negative means the force is downward, it will be what? It will be 0. Let me take it. Let me take outside. Okay. So let's go up here. So when I said negative 90 and less than 90, I mean by this, it's in the first and fourth quadrant as follows. This would be the y direction. That's y direction, guys. So if the force in this direction, or maybe the force would be here. Okay. Or the force is in that direction. So the force will start from here until here. Okay. This would be what? This would be the positive work. Work in this case would be positive. Again, why? Because work, the component of force, would be in the same direction of displacement. This is displacement. And if we analyze force in this direction, it will be F cosine theta. F cosine theta will be in the same direction of distance. If we come here, if the force is upward, or down force, or this is force, sorry. So if the force is upward or downward, positive 90 or negative 90, work is equal to 0. If the work here in the third and second quadrant, it will be negative, which means this. Let me show you like this. So here, if the force in this direction or the force in that direction, okay, guys, if you analyze it, the component of force will be like this. The component of force will be in this direction. Okay, and you will see that the component of force is opposite to the direction of displacement, so the work will be negative. I'll give you example in daily life for this. If the car is moving forward and friction force is in the opposite direction, friction is a force, and the friction force is all the time opposite to the direction of movement, so the work of friction is always negative. Friction force always perform or do a negative work, because friction most of the time is in the opposite direction again. So if the force has an angle between 90 or 70, which means in the second or third quadrant, the component of force will be opposite to the direction of displacement, and the work will be negative. The work will be negative. Okay, guys? So let's continue. Khalid. Khalid. خالد خالد بدر هنا يا شباب. كوميل.
Hello, Mr. Yeah, I'm here.
Okay. Khalid, would you read please this slides?
Yes, sure. Okay. Work can be positive, negative, or zero. Work is positive if the force has a component in the direction of motion. Work is zero if the force has no component in the direction of motion. Work is negative if the force has a component opposite the direction of motion.
Yes. And I mean by component F cosine theta. F cosine theta would be in the same direction of D here and in the fourth quadrant, and here in the third and second quadrant, the component of force will be in the opposite direction of movement. That's generally. This will be negative, and this in the top here will be positive, and this would be 0. Kumail? Kumail?
Yes, hello, mister.
Hello, Kumail. Can you read this, please?
Work. When more than one force acts on an object, the total work is the sum of the work done by each force separately. For example, if F1 does work W1, force F2 does work W2, force F does work W3, and so on. The total work equals work total equals work 1 plus work 2 plus work 3, and so on.
So I want something here. Work, guys, is a scalar or vector quantity? Anybody knows? We know that work equal force multiply displacement. Is it vector or scalar quantity?
Victor.
Vector. Work is vector quantity?
Yeah, because it has displacement.
No. Work is a scalar quantity, it's not vector quantity. Okay? So when we add work added on object, we add it algebraically, like negative and sign and negative and positive and so on. We just add them as scalar quantities, not vector quantities. So if we have an object, when more than one force acting on the object and each force exerting work on the object, what we have to do to find work done by force 1 and work 2 done by force 2 and so on, and we add them algebraically, W1 plus W2 plus W3 and so on. So it's not vector adding, it's only scalar quantity adding. طيب. Mishal, what's the time right now, guys? Mishal? Mishal?
Yes, Mr.
Okay, can you read this slide, the last slide that will take it in this session?
I start from where precisely?
From the beginning.
When work is done on an object, the object changes. For example, when you push a shopping cart, your work goes into increasing the cart's kinetic energy. When you climb a mountain, your work goes into increasing your potential energy. Thus, kinetic energy is energy of motion. Potential energy is the energy of position or condition.
Yes. I say position, this would be gravitational potential energy, for example, or elastic potential energy, or condition. So this is called the potential energy. This is the second lesson. We have finished the first lesson, and this is second. We will continue with the second lesson, inshallah, in the second session. I will start in the second session with a quiz on work, only work. Okay, guys? So see you in the second session, inshallah, after the prayer time. Thank you, guys.